So far in our work we've been looking at solving linear second order differential equations with constant coefficients in the form a d2y by dx squared plus b dy by dx plus cy is equal to 0. All of the cases we've looked at have had the right hand side equal to 0. We're going to now look at solving when we have the right hand side equal to a function of x. So we get a d2y by dx squared plus b dy by dx plus cy is equal to a function of x. The top one's called a homogeneous, the bottom one an inhomogeneous differential equation. Those terms are less likely to be used in further maths, but if you are doing any research you might come across them. We found a solution to this. The general solution was called the complementary function. When we solve a second order differential equation when the right hand side is a function of x, our general solution is y is equal to the complementary function plus a particular integral. The complementary function satisfies the equation when the right hand side is equal to 0. The particular integral satisfies the whole equation when the right hand side is equal to the f of x. So therefore the general solution becomes the sum of the two. In this video we're going to look at techniques that you may look to employ to find the particular integral, and there are a few different types, and once you get going it's fairly straightforward and you'll see the pattern emerging. So let's go at a few of these and see what we've got. So we're asked to find now the general solution of differential equation d2y by dx squared minus 5dy dx plus 6y is equal to the f of x, when the f of x is equal to a3 b2x c3x squared de to the x and e13 sine 3x. Okay, so let's write this out. So d2y by dx squared minus 5dy by dx plus 6y will be equal to 3. We first find the complementary function in the exact way that we've been looking at in the previous videos. We solve this equation when the right hand side is equal to 0, and we know that we can do that using the auxiliary equation. And in this case the auxiliary equation will be m squared minus 5m plus 6 is equal to 0. Factoring, we'll have what m minus 2 and m minus 3 is equal to 0. So the complementary function we could write now is a e to the 3x plus b e to the 2x. If that's new to you, please do check the videos on that. So there's a complementary function. That is the solution to the differential equation when the right hand side is equal to 0 and a and b are arbitrary constants. We now need the particular integral to add to the complementary function to get our general solution of this. What we do is what we call a trial function, and that terminology you don't have to remember, you just have to think about the process. When we have a constant that we could call k, what we'll try for our trial function is y is going to be equal to p. Now I'm saying p is a constant that has nothing to do with the particular integral, but p in particular integral, I've just chosen it for a constant. You might want to say that it's y is going to be equal to lambda. Okay, it's entirely up to you. So let's look at it in this case. I've got a constant and what we've got is y is equal to p. The first derivative dy by dx will be equal to 0. If you differentiate a constant, it's going to be equal to 0. And the second derivative d2y by dx squared will certainly also be 0. I hesitated because there's a quicker way of doing this particular example, but what we'll do is just work through the process as this applies to all of the ones that you're going to do. Essentially what we do at this stage is put these values into the differential equation and then find the value of p and form our particular integral. The thing is with this one, it's so blindingly obvious what it's going to be, it's often easier just to go straight at it. But the general process is we know that we're going to feed this in. My approach is as follows. I say I've got 1 of those, minus 5 of those and 6 of those. That will satisfy this differential equation. You might have to show that in your workings, so do check with your teacher or your exam board if this is perfectly fine. If I look at this, I can quite clearly see the only thing that I'm going to get is 6p. These are going to give me nothing. So therefore 6p will be equal to the constant, which is going to be 3. therefore p will be equal to 1/2. So I can now say that my particular integral is equal to 1/2, and the general solution, therefore, of the differential equation is the complementary function plus the particular integral ae to the 3x plus be to the 2x plus 1/2. But as you can probably see right now, you can do that by inspection, but it's not always going to be the case, hence why I've shown this approach. So let's look at it now when the left-hand side is the same and the right-hand side is equal to 2x. So d2y by dx squared minus 5 dy dx plus 6y is equal to 2x. And now our function of x is linear. So we know the complementary function. We've already established that the complementary function will be a e to the 3x plus b e to the 2x. What we now need is the particular integral, and we can set up our trial function. So trial function, just here. Consider now that we've got a linear function here, and we could put this in the form kx. If that's the case, I'm going to say that y, and we'll try y is equal to px plus q, where p and q are constants. So I've got kx. You might want to write now that you've got, for example, if you want to write, you've got lambda x plus mu. In this case, I prefer to just say, well, it's a function of x, so we're going to try px plus q. Okay, so what we'll get now is dy by dx, differentiating px plus q with respect to x, will simply give me p. The second derivative, d2y by dx squared, will be giving me 0. Differentiating a constant is 0. Now consider feeding this into the differential equation. We're going to have one lot of this one, we're going to have minus 5 lots of this one, and we're going to have 6 lots of that one right there. So what we end up with now, looking at the terms in x, we're going to have 6px, and then looking at the constants, we got 6q minus 5p. So we get 6q minus 5p. If we consider our function here on the right hand side, we've got 2x, so 6px is equal to 2x, and then we've got no constants, so we've got 0. From this, 6px is equal to 2x. As far as I can see, p will therefore be equal to 1/3. That looks good to me. And then we can sub 1/3 into here and solve for q. So 6q minus 5/3 is equal to 0. Add 5/3 and divide by 6. What's that going to give me? Q is going to be equal to 5/18. Therefore, I can now look and rewrite my particular integral. P is a third, so we end up with a particular integral of 1/3 x plus the constant of 5/18. General solution is equal to complementary function plus a particular integral. So in this case, y will be equal to ae to the 3x plus be to the 2x. Did I write 3x there? Hopefully I've written 2x. Be to the 2x plus 1/3 x plus 5/18. So there now is the general solution to the differential equation where a and b are arbitrary constants. So in this case, trial function, if we got a function of x as kx or some linear term, we can try y is equal to px plus q, or you might want to just try lambda x plus mu, entirely up to you. Okay, let's look at now when we've got a quadratic term. So we've got now d2y by dx squared minus 5 dy by dx plus 6y will be equal to 3x squared. We know that our complementary function is going to be now m squared minus 5m plus 6 is equal to 0, and we've seen as a result the complementary function is going to be equal to ae to the 3x plus be to the 2x. Please note that the reason I'm not going through this process, well, I just have then, but each time is because we got the same thing. Please don't fall into a trap of merely finding the particular integral. We need the complementary function, and that's the complementary function is when you're just solving this differential equation when the right hand side is set to 0. So there's complementary function. Particular integral. In this case, what we're going to do is our trial function, and we're going to have a quadratic in x. So if I say this is going to be some quadratic kx squared, we will try y is equal to px squared plus qx plus r. Therefore, dy by dx will be equal to 2px plus q, and the second derivative, d2y by dx squared, will simply be 2p. There we have the basis of our particular integral. Feeding this back into the differential equation, we've got one of these, we've got -5 of those, and then we've got now on this 6 of these. So what's that going to give us? That's going to give us now terms in x squared. We will have 6px squared. Terms in x, I'm going to have 6qx minus 10px. So 6qx minus 10px. Pxq, no, just px will be fine, I think. Don't know where the q, I wanted to write a q from. Didn't mean to. Now let's look at constants. We're going to have 6r minus 5q, and then we're going to have plus 2p. And let's consider what we've got here. Now in this particular equation, we've got 3x squared. We've got no term in x and no constant. Often you will have those. So 6px squared is equal to 3x squared. 6qx minus 10px is equal to 0, and the constant's also equal to 0. So from this, what we can see is quite clearly p is going to be equal to 1/2. 3 divided by 6. 6p is equal to 3. P is equal to 1/2. Now, if p is equal to 1/2, we want to find the value of q. So what we can say in this case now is 6q minus 10p is equal to 0. We've got p as a half, so 6q, and what's that going to be? Minus 5 is equal to 0. So q is going to be 5 over 6. So there's q. Q is equal to 5 over 6. Finally, we can find the value of r by plugging those values back in. So 6r minus 5q, which will give me 25 over 6, plus 2p, which is going to give me plus 1, will be equal to 0. So 6r will be equal to 25 over 6 minus 6 over 6. So what's that going to give us now? We're going to have 19 over 6 divided by 6, which will give me 19 over 36. That looks good. So r is equal to 19 over 36. Therefore, we can write our particular integral. We've seen that I put it in the form here, px squared plus qx plus r. We can simply write it now as equal to 1/2 x squared plus 5 over 6x plus 19 over 36. To get our general solution to the differential equation that we started with just here, we know that the general solution, we can write gs is equal to complementary function plus particular integral. So all we need to do is add them together. So we will end up with, and I'll write it down here out of the way, y is equal to ae to the 3x plus be to the 2x, complementary function, plus particular integral of 1/2 x squared plus 5 over 6x plus 19 over 36. And that provides us now with the general solution to the differential equation where a and b are arbitrary constants. So that's the type now where we've got a quadratic. So your trial function, if you've got a quadratic, you could try some form. Again, you might want to try different letters there. It's entirely up to you. Okay, let's now look when we have an exponential. So what we've got now, and we'll look at two different cases of exponentials. This is the nicer one, it looks like. d2y by dx squared minus 5 dy by dx plus 6y will be equal to e to the x. Again, we would need the general solution to be the complementary function plus a particular integral. So if you were going at this question from the start, you would show your full workings m squared minus 5m plus 6 is equal to 0. And we realised that the complementary function was coming up to be ae to the 3x plus be to the 2x. And now what we're going to find is our particular integral. If we've got this in the form now, and we'll do our trial function. So our trial function now is given as, and we'll take this to be ke e to the x, then what we'll try is y is equal to p e to the x. The derivative dy by dx will be exactly the same. It will be p e to the x. If we differentiate e to the x, we get e to the x. d2y by dx squared will be equal to p e to the x. Just be careful, if this is a case where we've got 2x here, just make sure that you're multiplying through by the derivative of the inside function. So it will hold. So for example, if we had p e to the 2x, then we'd have 2p e to the 2x, 4p e to the 2x. We've got one of those, we've got -5 of those, and we've got 6 of those. So let's consider what we've got. I've got 6p minus 5p plus p, which I make 2p e to the x, will be equal now to e to the x. That leaves me that 2p is going to be equal to 1, p is going to be equal to 1/2. Therefore, my complementary function, my particular integral, sorry, is going to be 1/2 e to the x. Remember, this capital P and this lowercase p are not related at all. I'm just using this for my values. So general solution, y is equal to complementary function ae to the 3x plus be to the 2x plus now 1/2 e to the x. And it was the nice case. What we're going to look at shortly is the case when this is also, so the particular integral also forms part of the complementary function, and we have to use a different method, as we can't have it part of complementary function and the particular integral. So there we go, that's that one sorted. So if you've got an exponential function, first try ke, if we got it in form ke to the x, try y is equal to p e to the x. If it doesn't work, multiply through by x. If it still don't work, multiply through by x squared. And that's what we're going to do shortly. Okay, let's now look at this one. This one is a trig one. So what we've got then is d2y by dx squared minus 5 dy by dx plus 6y is going to be equal to 13 sine 3x. In this form, we've got a trig function on the right hand side. So we know the complementary function by now is going to be ae to the 3x plus be to the 2x. We now need the particular integral, and we can look at these in a couple of different forms. And what I'm going to write now is our trial function, and it's entirely up to you how you want to structure this. We could say that we're going to have in fact, let's go for D and E. We'll do D and E. So let's go for d cos kx and then plus e sine kx. That's not e as in the exponential, it's just a constant. If we have something in this form, now bear in mind d or e could be equal to 0. In this case, we've got that d would be equal to 0. If we've got this case now, what we try is y is equal, and I'll write it here, let's go here, y is equal to p cos, and then we're going to have kx, and then we'll have plus q sine kx. This would be our trial function, okay? So d and e could be equal to 0, but we would still, even if they were, try y is equal to p cos kx plus q sine kx. So in this particular example, what I'm going to be trying is the following. I'm going to say y is equal to p, and then we're going to have now cos, and the k right here is going to be 3x plus q sine 3x. So in my case here, the value of k is going to be equal to 3. Again, you can use any constant there. So y is equal to p cos 3x plus q sine 3x. Be very careful right here, because we need to be able to differentiate trig functions. dy by dx will be equal to minus 3p sine 3x plus, and what we're going to get here, 3q cos 3x. Taking the second derivative d2y by dx squared, we now need to differentiate negative 3p sine 3x. Remember, p is a constant, so we're going to end up with negative 9p cos 3x, and then on this one we'll end up, what's that going to be, negative 9q sine 3x. This right here will form the basis of our particular integral. So what we get, we'll have one of these, we'll have minus 5 of those, and then we'll have 6 of these. My approach right now, maybe you want to show a bit more working, but my approach now would be to look at terms in sine 3x. So let's consider now what we'll have here. Terms in sine 3x, we're going to have minus 9q sine 3x. If we look at this one, we're going to have plus 15p sine 3x. And if we look at this one, we're going to have plus 6q sine 3x. And that must be equal to, now, we've got 13 sine 3x. If we now look at the terms in cos 3x, what we've got now is minus 9p. Then in this one, what are we going to have? We're going to have minus 15q. And then in this one, we're going to have plus 6p. And that will be equal to 0, as we've got no cosine for x's just here. These are now simultaneous equations, and I'm going to tidy them up. What I'm going to do is, say the top one, just tidying this up, is going to be 15p. What are we going to have? Minus 3q will be equal to 13. And the bottom one, minus 15. In fact, let's write this different. We'll put the p's at the front. What we can have on that one, we're going to have minus 3p. So minus 3p minus 15q is equal to 0. So all we're doing is solving these simultaneous equations. So let's, what should we do? Multiply the bottom one by 5. So equation 1 stays 15p minus 3q is equal to 13. Equation 2 will become minus 15p minus 75q will be equal to 0. So if we add these, what we'll get now, we'll add them, we'll get minus 78q will be equal to 13. Okay. 13 into 78 will go 6 times, so q will be equal to minus 1 over 6. So there's the value of q right there. We can find the value of p by subbing this in, and I'll put it into this one right here. We've got minus 3p, and then we've got plus now 15 over 6. I've got 15q here, so we can have now plus, what's that going to give me, 15 over 6, and that's equal to 0. So solving, what we're going to have then is 3p is equal to 15 over 6, and then divide through by 3. P is going to be equal to 15 over 18. We can take a common factor out of that one. Take a common factor of, what can we take out? 3, can't we? So p will be equal to 5 over 6. Therefore, remember, our particular integral was in the form now p. We've got p cos 3x plus q sine 3x, and that's what we looked at just here. That's where we started. So if we now plug those in, what we're going to get is the following. Our particular integral is going to be now, p is going to be 5 over 6, so we get 5 over 6 cos 3x minus 1 over 6 sine 3x. So this is our particular integral right here, and that is a bit laborious. So what we can say now is the following. We can say y is equal to the complementary function plus the particular integral. And let's just move that down because we'll want some space. So y is going to be equal to the complementary function, which we know is ae to the 3x plus be to the 2x plus the particular integral, which is going to be 5 over 6 cos 3x minus 1 over 6 sine 3x. And there we go. That is the general solution to the differential equation that we started with up the top. So as you can see with that one, it's just a bit more work, but hopefully that's made some sense. We'll finish off with the last example. Now, when we spoke before, I stated that the solution to the particular integral couldn't be part of the complementary function. So if we consider now what we're going to have with this bit one, if we said that the general solution now was the complementary function plus the particular integral, we already know it's exactly the same. We can say that the complementary function is going to be ae to the 2x plus ae to the 3x plus be to the 2x. you can see now that this is going to give us some form of one of these from the complementary functions. Therefore, if we have now ke to the x, and this is generally speaking ke to the x, and our trial function, we will first try the ke to the x, but quite clearly we're going to end up with the same answer, or the same the same as one of the parts of the complementary function. So what we try then is y is equal to, and you might want to write a, or I'm going to use p, we use px, so y is equal to px e, and in this case to the 2x. So in general, if we've got it in the form ke to some e to the some value of x, then we could do the trial function like so. So this is going to be y. So we've got y is equal to px e to the 2x. Now we're going to have to differentiate this, and differentiating I'm going to need to use the product rule. So dy by dx, we'll write it here, and I'll do my working down here. So what we're going to have then, using the product rule, we'll have px, and then we'll have p, and then what we'll have now is e to the 2x, and then 2e to the 2x. So if we look at the derivative of this, what we're going to end up with then is p e to the 2x plus 2px e to the 2x. So that's the derivative here. So what we end up with now is p e to the 2x plus 2px e to the 2x. What we now want is the second derivative, d2y by dx squared. Now consider the following. We looked at differentiating. In fact, you can go through the whole process again, but we know that the derivative of pe to the 2x is equal to this. So if we've now got, in fact, I'm just going to do it rather than try and confuse. Well, say confuse. Do it all again. So let's just consider now, if we differentiate this, we'll have 2p e to the 2x. Essentially what I was saying was the fact that we can spot that's exactly the same as that and differentiate again. I'll just go through the process. So we've got 2px, and then we'll have 2p, and then we'll have e to the 2x, and then we'll have 2e to the 2x. So we're going to end up now with 2p e to the 2x plus 4p x e to the 2x, and then we can add it to this. So you can see by adding this, we're going to end up now with d2y by dx squared is going to be 4pe, so let's change that to 4, plus 4px e to the 2x. But please do use the quicker method I was alluding to just there. So that's what we get. So using product rule, these are derivatives. Okay, so now what we can do is set up the particular integral again. Going back to our differential equation, we know that we've got, and we would sub this in, and you might again want to show this being subbed in. I've not done it as yet, but you might want to do that. So we've got one of these, we've got minus 5 of these, and we've got now 6 of these. The way I look at this now is as follows. I appreciate that you should go through the whole lot, but what we're looking for, we've got this in the form now, e to the 2x. So if we think about this, we're not going to want anything now with an x. So what we can do is the following. We can look for terms independent of the x. And if we look, we've got one of those, and then we've got minus 5 of those. So 4p e to the 2x minus 5p e to the 2x will give us minus p, and then what we're going to have is minus p e to the 2x, and that's going to be equal to e to the 2x. So we can see from here that p is going to be equal to now minus 1. Okay, so what we can do from here is simply use this now in as our particular integral. So our particular integral is going to be now, so complementary function, let's write this out, it's been a bit messy, a e to the 3x plus b e to the 2x. Particular integral now is going to be, we know that p is equal to 1, so we're going to have minus x e to the 2x. As stated, if x doesn't work, go through by x squared. So what we end up with now is our general solution, y is equal to a e to the 3x plus b e to the 2x minus x e to the 2x. And that is the general solution to our differential equation, where a and b are arbitrary constants. Hopefully that's made some sense. It's a bit sketchy, the last bit, but hopefully you can see. If we can see that this is also going to be what part of the complementary function, then we need to multiply through by x. If it still doesn't work, go through by x squared. So they're all the particular types. It's taken us a fair while, and I'm kind of getting a little tired, as you can probably imagine. But that should see you through, and this will allow you to solve any of the linear second order differential equations in FP2.